Is this good? Sound? So as we said, it's mainly tutorial style. We don't expect people to know about quantum computing. The goal actually is to introduce people to quantum computing, as well as have some people from the community who has been already working in quantum computing to share with us their work, so that this can incentivize people to work more in quantum computing. Personally, I believe that it's coming very fast, and actually this is the time to enter the quantum computing. And as I'll show in the talk, this is not just a personal opinion. Many of the industrial leaders have the same vision. Good. Any questions before we start? Very good. So in general, quantum technologies can be divided into 3 areas. Quantum computing, which is the focus of this workshop, includes different algorithms for solving problems as compared to classical computing. Quantum communication, where you want to transfer quantum information between different quantum devices, quantum computers. So this is mainly communication and networking people are interested in. And finally, quantum sensing, where you have sensors that leverage quantum phenomena in order to provide much higher accuracy for sensing, for example. And again, this is a different area, and these are the 3 main areas for quantum technologies. As I said, our focus in this workshop is in the first area, which is quantum computing. So what is quantum computing? Quantum computing is a new field that lies at the intersection of physics, computer science, and mathematics. So basically, we leverage some phenomena from quantum mechanics in order to perform commutations in a much more efficient way compared to classical computing as we know it today. For example, you use superposition, interference, and entanglement, and so on, and we'll give you examples about what these mean and how we can use them for communication. Currently, in quantum computing, we have like 2 main branches. So these 2 branches falls under quantum computing or quantum algorithms. The quantum circuit model, you can think about it as the general quantum computing programming. This is what quantum computers are. If you want to have a general algorithm for quantum computing, this is what people use. It's quantum circuit model or quantum gate model. But there is also quantum annealing. And if you are familiar with optimization, this is the quantum version of simulated annealing. So simulated annealing is a classical algorithm for optimization. There is a quantum version that provides enhancements in terms of the speed and so on. And actually in this workshop, we are going to cover both of these models, the general circuit model and the quantum annealing. I'll be talking about the general circuit model, and Ibrahim will be talking about the quantum annealing part. Any questions so far? Great. So why now? Why quantum computing? If you have been following the news, actually almost every day there are new news about quantum computing. Some of the news is Shor algorithm has put our current encryption methods at risk. So Shor is a professor at MIT who's one of the leaders in quantum computing. And actually he came up with an algorithm that can can factor integers in a very efficient way in polynomial time. Why this is important? Any idea, any hint? Why factoring integers is important? Yes, encryption, because the current algorithms that we are using in our daily life to encrypt our communication, emails, social networks, bank transactions, and so on, are based on the RSA algorithm, for example, and it's at the core of it is factoring large integers. That factoring is a hard problem. Why? Because actually the best known algorithm on classical computers, it's believed to take exponential time, so it takes a lot of time, and we leverage this to secure our computations. However, Shor came up with an efficient algorithm that can run in polynomial time on a quantum computer that can factor integers, and by doing this, all our current encryption as we know of today is broken. And actually maybe 1 year ago, Microsoft and Google announced that they are integrating in their operating systems both quantum algorithms for security. Meaning, if we have quantum algorithm, the current encryption is broken, so we need to search for new algorithms to secure our communication again. And actually, it is not something they're thinking about. They are already integrated in the Windows operating system and in the Chrome browser, both the quantum algorithms. So sure, algorithm breaks the current encryption methods. Quantum key distribution will make encryption safe again, which is a quantum version of the classical algorithm. Grover algorithm is another algorithm for searching an unsorted list. So classically, if I want to search an unsorted list, what is the complexity of that? Any guesses? Linear time, it's order n. Thanks, Carol. So Grover can do it in a square root of n. It is not a big enhancement, but actually the ideas in the Grover algorithm, as we'll see, thinking in a quantum way is not straightforward. It's a completely new way of thinking, and we'll show you today some of these examples. So the idea that Grover came up with to come up with this square root of n algorithm for searching a list are interesting and general and can be used in other quantum algorithms. So you learn also other things from other algorithms. Again, China teleported a qubit from Earth to satellite. So we talk about quantum teleportation, and actually today I'm going to show you the quantum teleportation algorithm. Very nice, very simple algorithm. Google claims quantum supremacy. What does this mean? That quantum supremacy is when you come up with an algorithm that solves a problem that will take a classical computer thousands of years, but on a quantum computer you can solve it in a few hours, if not minutes. So this is what they call by quantum supremacy, that you show the advantage of the quantum computing algorithm. So a few years ago, I think in 2019, Google claimed quantum supremacy. We had this quantum algorithm that can efficiently solve problems, but of course, this is a big thing. The one who claims that they achieved the quantum supremacy, it's a big news. So other people like IBM, no, they have a loophole and it is not really quantum supremacy and so on. Actually, just last month, Google again announced that they have a useful quantum algorithm that outperforms supercomputers. So they can, the problem is called the quantum echoes. If you are interested, you can Google it. And it takes 13,000 times longer on a supercomputer. So in a classical supercomputer, it takes more times compared to a quantum computing algorithm by 13,000. So this is real quantum advantage. Actually, this is a real problem. It is not just an artificial problem. And as I mentioned, each day you have more news coming about quantum computing. Last year, I think in 60 Minutes, so 60 Minutes is a very famous talk show in the USA. They interviewed the head of quantum computing, IBM and Google. And in this, it's an interesting show to watch the current trends. And both of them agreed that we don't need any more fundamental breakthroughs. Actually, everything, we have all the pieces and we need to put them together. So it is not a matter of if quantum computing is going to happen or not. It's actually a question of when. And according to the head of IBM Quantum and Google Quantum, actually this when is before the end of this decade. It's before 2030. We are talking about 5 years for this to happen. And they actually, if you are following the news of quantum computing, this is happening very fast. And actually that's why it is important to go and start in this interesting field today, not tomorrow. Any questions? Good. Just some numbers about what is the market share and so on. So this is a report from McKinsey and the company. So the market share is expected to by 2040 to reach 173 billion US dollars. As we said, quantum technologies in general are 3 areas: quantum computing, quantum communication, and quantum sensing. So actually the majority of this, $131 billion out of 173, is about quantum computing. It's a huge market share. Quantum communication is still 36 billion and the quantum sensing is 6 billion. So there is a huge market share. Not only this, in the same report, McKinsey found that for every 3 quantum jobs opening, there is only 1 qualified candidate to fill this job, which means there is a lot of demand for people with quantum computing expertise. You can only fill 33% out of the demand in the market. And they expect by this year that 50% of the quantum jobs will be fulfilled. So for your students, if they are, or for young people who are here, if you are starting your career in quantum computing, you have a big opportunity to find jobs after you graduate. So time is now to invest in quantum computing as an individual and as institutions. Great, so I hope I motivated you about quantum computing and why it's important to start learning about it. So let's go some technical. So what is quantum computing? As we said, it's a field at the intersection of quantum physics, computer science, and mathematics. As we'll see in this workshop, it's an entirely new way of thinking about computations. It is not that you take a classical algorithm like integer factoring and just you run it on a quantum computer. It doesn't work this way. Actually, you need to think about the problem in a completely different way in order to come up with an algorithm that can work on quantum computing. Once you do this, you can efficiently solve and break hard problems on classical computers. And this includes, as we mentioned, encryption, searching, optimization, and many more. So the basic unit of computations in a quantum computer is the qubit. Qubit is short for quantum bit. So a quantum bit is the basic unit of computation. What is a qubit? It is similar to classical bit. So a classical bit that you are used to work with in our classical computers can be in one of two states. It can be either 0 or 1. The light can be on or off. This is the classical computer. But actually, what is interesting here is the qubit can be in a superposition state between 0 and 1. So actually, when it's in a state, you can think about it, it's in a mix between 0 and 1 at the same time. So it is not pure 0 or pure 1. You can think about it's 90% 0 and 10% 1, or 80% 0 and 20% 1. So it's a mix between 0 and 1, and actually this is the property we call superposition. So the superposition state between 0 and 1 at the same time. When you measure it, so actually at any point in time, it's in a mix between 0 and 1. But when you measure it, what will happen? It will collapse to a classical 0 or classical 1. So at any point in time, it's in a mix, but when you try to measure it, it will collapse to a classical 0 and 1. And that's why actually our world is not based on what? It will be 0 and 1. It's probabilistic. So if the mix was 90% 0 and 10% 1, when you measure it, it will be 0 with 90% probability and 1 with 10% probability. Okay? And actually that's why, as we said, our world is, our best understanding of the world now is governed by quantum mechanics. And it's a probabilistic theory. So why are we not seeing things randomly in the environment? Because actually when we are looking at things, we are measuring. Our eyes are measuring them. And when we are measuring them, they collapse to classical 0 and 1. Make sense? Actually, it's very hard to imagine. And as we'll see, big people like Richard Feynman, for example, one of the winners of the Nobel Prize in Physics for their contribution to quantum mechanics. So quantum mechanics and quantum physics says that if you think you understand quantum mechanics, then you don't understand the quantum mechanics. It doesn't mean that it's actually, there are many things that are not counterintuitive. We are not used to them in our daily life. That's why it is a new concept and interesting concept. So again, a qubit as compared to a classical bit can be in a superposition, can be in a mix between 0 and 1 at the same time. When you measure it, it will collapse to 0 and 1 with probability depending on the amount of the mix before you measure it. And actually this is a destructive process, meaning once it goes to a classical state, you cannot go back to the superposition again. So measuring is destructive, and it's important to remember that. Entanglement, we'll talk about entanglement, but it's basically a correlation between two different qubits. A good analogy that actually helps me at least visualize or have an idea what the superposition property is, you can think about a coin. So when you toss a coin, what happens? It's flipping in the air. So when it's flipping in the air, is it 0 or 1? I don't know. It's a mix of 0 and 1. It can be 0 and 1 at the same time. But once it lands, it will be either 0 or 1. And this landing is the measurement process. So once you measure it, you will get head or tail, and this is probabilistic, depending on whether it's a biased or an unbiased coin. So it's a good analogy to relate the qubits with classical bits. So a classical bit, as we said, at any point in time, it can be in one out of two states. The two states are 0 or 1. So classical bit at any point in time, it can be 0 or 1. What about the qubit? How many possible states it can be in? So at any point in time, it can be in one state, meaning one mix. But one mix out of how many possibilities? Any guesses? Infinite. Why? Because actually the amount of mix is arbitrary. So it can be 90-10, it can be 80-20, it can be 0.75-25. So you have a continuous range of probabilities. So a qubit can be in one state out of infinite number of possible states, and which is much richer than compared to classical computing. So actually this superposition that you are being in 0 and 1 at the same time, when you do your operations on the qubits, you are operating on 0 and 1 at the same time. And actually this is what we call quantum parallelism. Because in one operation, you are working on 0 and 1 at the same time because your state is a mix of 0 and 1 at the same time. And this is what allows us to gain, in some algorithms, exponential speeds, and we'll show some examples today in the workshop. Any questions so far? Muhammad.
Will we be getting the slides?
It's okay with me, so no problem. I'm not sure about Ibrahim.
Yeah. We can upload it on the website. And how about the recording? It will be public. That will be only. Thank you.
No. Great. Moving on. So as we said, the measurement process is destructive, meaning that once I measure, I am in a superposition state, but when I measure, I collapse to classical 0 or 1 with probability, and it's one way. If I collapse it to a classical bit, I cannot go back to the superposition. It's destructive. And actually, this is interesting in designing the algorithms. We'll come back to it. But actually, this probabilistic nature and the collapse of the measurement and so on is captured by a very simple and nice mathematical model. Actually, quantum mechanics in general is based on linear algebra. So linear algebra, you're talking about our world is linear. So the theories that is capture our best understanding of nature as we know it today is based on linear algebra. What about entanglement? So as we said, entanglement is a correlation between two different qubits. So I have two qubits, each one of them in a superposition state, but they are correlated. What does this mean? It means that when I do something on one of the qubits, something correlated happened to the other qubits. So for example, if you have two qubits, if I measure one of them and it collapses to 0, the other, for example, must be 0. So they are correlated. So when I do some operation on one of them, the first one can be 0 or 1 with certain probability. But if it turns out to be 0, the other one must be 0 because they are correlated. So this is what we mean by entanglement. But actually what is interesting about this entanglement is that it happens regardless of the distance between them. So I can have two correlated qubits, one with me here and the other is on Mars. And when I do a measurement for this qubit and it turns out to be 0, the other one instantaneously in 0 time jumps to 0, even though they have a huge distance between them. So two interesting implications. One is if something happens in 0 time instantaneously, this means that the speed is, Anton? Yes, infinite. If you divide by time 0, you get infinite speed. And the infinite speed is higher than the speed of light. And according to Einstein, the speed of light is the maximum speed you can have in the universe. So this is something Einstein didn't like about quantum mechanics or physics in general. It's a paradox, and of course, no. Entanglement doesn't allow supernomial communication. Supernomial communication means communication faster than the speed of light. And the other thing is, you do something here, and the other thing on Mars changes in 0 time, even though they are not in the same space. So actually Einstein also called this spooky action at distance. Something spooky is happening when they are separated by distance. This is another thing he didn't like about quantum physics in general. So again, he didn't like it, but it is correct. He didn't say it is incorrect. He thought that there are better theories that can understand how the world works. But actually he died. He had a theory before he died. And actually Bill, we'll talk about the Bill states today, inshallah. Bill came up and had a very interesting test to show whether Einstein explanation or actually the spooky explanation is the correct, and it turned out the spooky explanation is correct compared to Einstein explanation. Any questions so far about entanglement? Yes, please.
Can they also be anti-correlated?
They can be independent if this is what you mean by anti-correlated. What do you mean by anti? They can be in any form of correlation, yes. So actually, if you think about it, it's like the joint distribution. So you have two random variables, which is each individual qubit. And then the correlations, the entanglement is you are talking about their joint distribution. So it's exactly the mathematical models that capture entanglement. Oops. Great questions. Other questions? Good. So what is quantum computing? As we said, it leverages the properties of quantum physics like superposition, entanglement, and the measurement, plus human ingenuity to come up with new algorithms that can solve existing problems much more efficiently compared to their classical counterparts. And we'll see in this tutorial a number of examples. So is there a relation between classical and quantum computing? Are there two different disciplines, or there is a relation between them? Actually, classical computer is a subset of quantum computing. So quantum computing is the more general model. Anything you can do on a classical computer, you can do on a quantum computer. But the other way around, it is not clear. So is it a proper subset or improper subset? We don't know, but at least this is the more powerful model. Anything you can do on a classical computer, you can do on a quantum computer. And the qubit is the basic unit of computation, not the bit. And actually, this is how nature behaves. Yes, please, ma'am.
One computer and that computer compute exactly the same set of problems. There is no difference. The only thing is efficient in terms of polynomial, finite,
yes,
reasonable time, whatever you have there.
Good.
This is more.
Yes, thank you. Great. So yes, if you have a problem, you can solve it on both computational models, the quantum and the classical, but the question is which one is more efficient, and this is what Martin clarified. Thank you, Martin. Good. So actually, why now? Quantum computing, as we said, it has been maybe from 1960s or 70s. So they have been for maybe 50 years. Why they are in the news today? As any technology, it's because of killer apps. Because of the killer app. So as we said, there is a growing advancement in both quantum hardware and software, and there are big investments. As I said, all big companies, you name it, IBM, Intel, Google, Microsoft, Amazon, they are putting billions of dollars to make quantum computing a reality. NVIDIA, actually maybe last year, if you are following the news, the CEO of NVIDIA came up and said quantum computing is not ready, it will take 20, 30 years to become a reality. And the stocks of all startups and the big companies dropped in one day by billions of dollars. But actually 1 week later, he said, we are establishing a quantum computing unit in NVIDIA, and we are hiring for it, and we are hiring for it. So actually it's a contradicting signal, but actually everyone is investing in quantum computing, and many startup companies. All of them, actually the way I think about it, it's like classical computers in the 1670s and 60s. You had mainframes, we have very big computers, we don't know whether it's going to work or not. Actually today is the processor in my cell phone is much more powerful than the mainframe computer that existed 20, 30 years ago. I think we are in the same state in quantum computing. Different companies are trying different technologies to make it happen, but hopefully in the future, maybe we have QPUs in our mobile devices, quantum processing units like GPUs and CPUs, where you can solve, of course, quantum computing, I think, as we said, it's a general model, but in practice, at least for today, it is not suitable for all problems. So for some time, the classical processor and the quantum processor will coexist for some time. Some more recent news. So actually, HSBC, which is a famous bank, of course, is using IBM quantum computers to solve some algorithm, I think, in stock prediction or something like that. The Volkswagen is using quantum computers to solve also problem, I think, in their pipelines and so on. So again, it is making very fast progress. State of Maryland and University of Maryland are announcing $1 billion capital of quantum initiative. Today, Tony Blair, I think, said if we don't catch the quantum wave, we'll be sorry. In UK, all countries now are joining the quantum race. UK and US seal take back with 31 billion for a high-end quantum push. Qatar in the Middle East, and so on. Why NAM, as we said? Because of the killer apps. So one of the main killer apps, as we said, is the Shor's algorithm. Shor algorithm breaks the current security of all algorithms that we know on the internet, your bank transactions, emails, and so on, and this is a big thing. Grover algorithms for searching unsorted lists. We are talking about also quantum machine learning, where you can use quantum computing to speed up training of machine learning models. Several institutes claim the quantum supremacy, Google, universities in China, and so on. And as we said, we are talking about the end of this decade, within 5 years, not 10 or 20 years. Any questions so far?
I have a question.
Please.
I remember that this was brought to my family about the topological unit Microsoft. Do you know how you should do it?
This is algorithm or this is the hardware? So I'm not following the hardware news. What I know is there are different ways, different technologies at the hardware level to try to have quantum computing hardware to do that, but I'm not following the news. So, but there are many companies, as I said, with different technologies trying to make it happen. Thank you for the question. Other questions? Good. So I think this is a quick introduction. Maybe I can switch to Ibrahim now to start the quantum annealing tutorial, and then I'll come back and talk about the general circuit model after Ibrahim finishes his part. Thank you.